See your slides.
Excellent. I will get started straight away. So first of all, it's a pleasure for me to be here. It's a happy moment for me to see the occurrence of this workshop on my favorite programming language conference. So I'm very grateful to the chairs for organizing this. So I will be talking about eFLINT, which is a language, a domain-specific language for describing norms in a general sense. One of the main goals of the language was to be able to execute specifications. So executability is an important aspect, and also to be able to use it in a wide variety of applications. What I'll be talking about is mostly how we can think of eFLINT as a sort of intermediate language, like the sort of legal calculus that the second speaker today mentioned. So the language meets many of the properties that were laid out in that presentation. And I think it can be used as a way to also give a formal semantics and an execution framework for DPCL that Giovanni just talked about. So these are some of the contributors to the language. So my obligation or my task has mostly been the design and implementation of the language inspired by conversations with Giovanni, our previous speaker, and Tom van Ers. And PhD students have been working on applications and case studies. And I'll start with trying to explain the connection between normative and computational concepts that is applied behind the language. And then I'll discuss several of the developments around the language and provide some general reflections. So the operational semantics that is given to the language is based on a plotcon style semantics. So that's we're thinking about transition systems. On the one hand, to describe the behavior of the system of which we want to check the compliance, but also to describe the possible evolution of the normative specification that we're looking at. So we're thinking about two transition systems and the relations between them. So we're looking at states in which variables are assigned truth values and transitions between states. And then for both, we can talk about violations. So particular states being violating and particular transitions being violating. So then we can associate the deontic concepts to these various components. So we can talk about prohibitions of states and prohibitions of transitions, same for permissions and obligations. And as Giovanni also mentioned, we are applying a potestative perspective as well, in which we have powers that might change the normative positions or to change the normative positions of the actors involved. So powers relate to transitions and by having normative consequences. So this is realized by making the deontic and potestative concepts first class, in the sense that we represent them as terms that can be set to true or false, and that can therefore also be affected by transitions. So applying the Wholefeldian perspective as well, we're talking about relations between actors, normative relations. So when we talk about the deontic terms, we have holders and claimants, and potestative terms, we have performing actor and the recipient that is affected by the power. The type of reasoning that we're doing with the language, so as I mentioned, the primary goal is to determine the compliance of a system. So we can write concrete scenarios that describe a single trace in the transition system that underlies the specification written in our language. And we can use that to reason about concrete scenarios both before and after the system is running. So ex ante and ex post assessment of our scenarios. But we also want to be able to, we can also use it dynamically, where the system is in a particular state, and we want to reason about a particular action. We can again do that beforehand or after the fact. So after the fact, that means executing the action and then reporting the findings on whether a violation has occurred, or trying or seeing what the effects would be of the action by trying the transition, and based on the details in the report, determining whether or not to actually execute the action. So that's also related with two types of enforcement, ex ante and ex post enforcement. What we are not doing yet is reasoning with abstract scenarios, where abstract scenarios in which we might have placeholders that describe sets of scenarios, which might be used for planning or checking certain properties of requirements. But we do have a project starting up with our students to pick this up. And this is typically where we can imagine translating to something like a model checker or a Z3 solver, where we're talking about concrete scenarios, we can imagine translating into LLVM, which was discussed as well. So let's dive into some of the details of the language through an example. So the language consists roughly of, let's say, two sub-languages. The first part it consists of declarations, where we write a specification, which determines that transition system. And we can write scripts or sequences of statements that describe scenarios. And we need a way to represent the knowledge. So for this, we have fact type declarations. So for example, the fact person here introduces a predicate over some strings. And then we can have predicates which are well, relations, in this case over two components. The placeholders here are essentially aliases or introducing names of variables. And then we can have derivation rules attached to our fact type definitions. In this case, saying that a legal parent, that someone is the legal parent of someone else if they are an adoptive parent or a natural parent. So this is like a logical implication that is being attached to this type in order to derive instances of that type. Now, to look at some normative concepts, we can also define act types and duty types. And for act types, we associate an actor and a recipient, as mentioned before, as actors. We describe the effects using creates or terminates clauses. And we can describe two kinds of conditions, conjunctive and disjunctive conditions. So holds when for disjunctive, and condition by for conjunctive. And duties, they also have the two actors, a holder and a claimant, and violation conditions associated with them. And we see here that the duty that is being described is one which is an obligation to do something, because if we look at the act help, we see that the duty is terminated by this action help. So then we can, in the context of this specification, we can write a scenario first by listing the particular atoms that we're going to be considering. So we specify the domain of discourse. We produce an initial state by declaring some initial facts, and then we can write statements like ask for help, which executes an action, makes a step in the transition system, an event that creates an instance of effect, again making a transition, or write queries that well, are expressions that are evaluated in the current state, etc. And in this way, a scenario unfolds, and any violations are being reported alongside the results of queries. So this is eFLINT version 1, let's say, as it existed roughly 2 years ago, with a basic web interface in which you can write these kind of specifications and scenarios and can get some feedback on them. Then, since then, quite a few things changed for, let's say, the second version of the language, in which the language was extended, in particular to support dynamic compliance assessment as part of our running system. And I want to discuss mainly the two extensions, on the one hand, the extends keyword and the syncs with keyword. So extends allows us to write declarations in a rule-like sense. So for individual articles, we can write down declarations. And there's also a way of including files and separating our specifications across files. And this way, we can support really making sure that we have separation of concerns, in the sense that we can write a specification that corresponds exactly to a file in the level of detail, the level of abstraction of the original file, and then write additional files for further specializations and concretizations, in which this extends keyword plays a crucial role, and also synced with in the way that I will describe. So the example taken from the paper that is mentioned here, we're looking at an article of GDPR, the European Privacy Regulations, where an action is described which is collecting personal data. There's nothing normative in the example here because there's no conditions, except we just see the different actors and objects involved in that collecting of personal data. Interesting to mention is that there's data is collected for a particular purpose. And the effect of this is that processing is occurring by a particular processor on behalf of the controller. This is the language used by the GDPR. And then we can use the extend mechanism to add conditions to this action. So following the Article 5 of the GDPR, we can see that collecting personal data it must be the case that the data is minimal for the purpose for which it is being used. Similarly, the data must be accurate for the purpose for which it is being used. And these can now be expressed separately in individual declarations. And yeah, because conditioned by is conjunctive conditions, they all need to be true simultaneously. Now, of course, these fragments don't actually say when data is minimal for the purpose or accurate. That's of course to be specified in addition to this. Similarly, for Article 6, which is a disjunctive article, we use the holds when clause to say that collecting personal data is legal. One of the reasons why it might be legal is if there's consent by the data subject for processing the data, or if there is a legal obligation for collecting the personal data. In this example, in this paper, we're looking at a use case around hospitals, where hospitals wish to exchange data among each other, and they use a registry at a particular one of the hospitals of the consortium for collecting all that data. And then we answer two compliancy questions related to the use of this registry. I will focus on the first one, which is what conditions need to be fulfilled by a member of the consortium, a particular hospital, for making data available to the registry. So here we see that where we previously looked at GDPR articles, now we see an example of an article from the consortium agreement between these different hospitals, which in some sense extends or imports the GDPR specification. Well, first of all, one of the articles here says that members can only transfer data to the registry in a coded form. So it's either anonymization or pseudonymization going on, which is expressed here by two conditions, one of which saying that the dataset must be coded, again specified somewhere else, and another which says that the institution or the organization making the data available must be a member of the consortium. So this is still separate from GDPR, but the two specifications are connected here, again using the extends keyword to add an additional clause to our make data available action using the syncs with keyword. So this says that if the make data available action is triggered, this needs to synchronize with particular instances of the collect personal data action, which comes from the GDPR, in the following way. So where we see that the institution that is making the data available is considered a controller in this processing. The processor is the Dutch Childhood Oncology Group. That's the organization that is running the registry. The purpose is the research into DIPG, which is the particular disease that this use case is about. And this actually happens for all the patients or donors which are identifiable in the dataset. So in this case, there would be multiple, the make data available instance would trigger multiple collect personal data instances. So now we can answer that compliancy question is when can an institution make data available? When they are a member and the data is coded. This comes from the consortium agreement. And when consent is given and the data is accurate for the purpose. So here we see how two different specifications come together. So one of the important observations as part of the design of this language is that, well, we're applying it in two different contexts now. On the one hand, for analyzing concrete cases without having an execution context, and we're also doing when we do have an execution context, when we apply specifications at runtime. These are rather different in usages, and one of the design decisions that I made in the design of the language to incorporate this is looking at when we enumerate instances of a type. So, for example, if we look at the expression that there is no person that still has homework due, we need to iterate over the set of persons. So the first option, which was used in the, let's say, the first version of the language, is that we enumerate the possible instances of this type. So we list in the domain of discourse, we have Alice, Bob, Chloe, and David, which can of course be enumerated. However, in a running system, we may not know which persons or users or administrators exist in the system. They can be added at runtime. So in that case, we might want to look at the knowledge base to determine which are the persons currently in the system. So when we're iterating over instances like this, what eFLINT actually does is to first look at the domain of the type, whether that's finite, and otherwise look at values in the knowledge base. And by making the design decision this way, we can still support both usages of the language. So we can use the same specification in both application scenarios. Another is that we observe that especially when specifications are used at runtime, we might want to just monitor for compliance. And so we just want to sort of passively make decisions about whether any rules have been broken without interfering the system. And in this case, we want the effects of actions to take place, even if they would cause violations, or even if the action was actually not enabled, so independent of the conditions associated with that action. However, we don't want to determine this upfront, so we want to support both scenarios. A number of other extensions that have been made to the original language on top of the ones that are already mentioned is that we can mix declarations and statements freely. So that allows actually to also create specifications at runtime, rather than just executing scenarios. There are open and closed modifiers associated with type declarations, which say that if a type is open, that means that there's essentially no default value. We need to have some additional input to determine whether an instance of a value holds true. So in a closed, for a closed type, that's under the closed world assumption, the default could be, for example, false. But in open, that means that the execution context need to provide an assignment to effect, whether it's true or false. And this enables many interesting things. So we can completely externalize the state of our reasoner. So if we make all the types open, we can use this as a mechanism to handle open terms. So to leave it to the execution context to determine, for example, what is considered undue delay. And well, to support these different changes to the semantics of the language have been made as well. Now, I mentioned on the previous slide eFLINT actors. So one of the consequences of this redesign of the language, or this extensions of the language, is that we can integrate our implementation of our language as an actor in a running system. We can have multiple instances of them, multiple instances of the same specification, or multiple instances of different specifications all at the same time in the system. And then other actors or components in the system, services, interact with our eFLINT actor by sending notifications about actions taking place, or facts about the world, the situation changing. And then the eFLINT actor communicates notifications about any violations that occur, or new duties, or new powers that come in play. Queries can be asked about whether permission to do something exists. And eFLINT actors can also send out queries in order to fill in these open facts, for example, to verify whether indeed a hospital or a healthcare provider has issued a certain receipt, for example. And the norms can change dynamically as well. Now, again, as a consequence of the different features that have been added to the language, we can support, let's say, an intricate process by which a specification is actually being used at runtime. So after the design of our language, we can use it to interpret natural language text to produce a specification, which can then be reused across various application contexts. For example, where in a banking application, clients are considered subjects according to the GDPR, but in a hospital application, this would be clients. But we can reuse the same specification. Then once we have our specification, we can combine it with observations about the current situation, which would be called qualification, to produce a scenario, which can then be assessed to produce a report. And the report then serves as an input for an enforcement decision. And we've done experiments which show a different part of this diagram. So what we have in terms of implementation is, well, a Haskell implementation, which I consider to be a reference implementation. So it's slow but correct, let's say. And it's correct because it's based on operational semantics, which hasn't been written as a formal operational semantics separately, but the way it is defined is very similar to that. This implementation gives us two executables, a REPL interpreter, which serves as the basis of Jupyter notebooks that we can run, and a server, which is a TCP server, which is then used by our Java implementation work to set up a TCP client and a HTTP server, in the end giving rise to these eFLINT actors that we use in the akka framework for doing actor-oriented programming. So that's where we've done most of our experiments for dynamic compliance checking. So I will conclude by responding to some remarks that I've collected over the years. So on the one hand, thinking from the perspective of a PL expert, it may seem that eFLINT is just a transition system which some extra conditions lying on top, which is in essence a correct observation. However, we have integrated certain normative concepts like the duties and the power concept and the relations between actors. And we have made sure that we can support the legal application domain in various ways by making sure that our extension mechanism is modular, that we can have this separation of concerns between files, etc. And a legal expert might say that law is subject to interpretation and has deliberate open terms. And with our language, we are capable, of course, of formalizing interpretations for which we can also have alternatives. So that enables a debate on specific formalizations of certain laws. And we have several mechanisms of dealing with open terms, like extending files, alternative files for giving alternative instantiations of open terms, and leaving open terms to be instantiated at runtime. eFLINT is still difficult to use for legal experts. That's certainly the case, and this is one of the primary goals of the coming months, is to work on the usability of the language in various ways. For example, working on extending our notebooks to have very specific support for particular domains and legal experts, and also thinking about design patterns, which was also mentioned during our keynote, which may either reveal themselves as certain widgets in our user interface or as higher level language constructs. So with that, I will end, and thank you for your attention.
And we have a Q&A question.
Yeah, so I failed to mention this, but indeed, if we consider exceptions, if we use negation of conditions as exceptions, then we can certainly describe articles in this modular fashion that I demonstrated, when these articles also explain exceptions, and we can even do that for exceptions on exceptions and so on. Now, defaulting is not something that I think about, so I wouldn't. That's not something I've considered, so that's something I will need to look into.
All right, and as we are about to wrap up this session, we have one last question, which is Jason asks, where can we go on the web to try eFLINT?
Yes, I will make sure that a link becomes available. So this very simple web interface is available, but it's for this older version of the language. And I think we can make notebooks available in a relatively short term as well. So I will make sure that I update the conference webpage with a link.
All right, well.